My name is Andrew Uselton with NERSC at Lawrence Berkeley. I'm going to talk today about statistical properties of Lustre server-side I/O. This is a work in progress. The goal of the research is to basically help Doug with his conversation that he alluded to in his talk, where he's trying to get people to spend more money on I/O and not starve the I/O system for the benefit of the buying compute. So I'm hoping that I'll be able to actually get a fairly rigorous relationship between what your workload is and what your performance is. And this is work in that direction. The goal of this talk is to get to where I can convince you that this is a useful diagram. So we'll see if we can actually get there before we all go to lunch. I know I stand between you and lunch, so I'll try to see if I can scoot through this. I'm going to talk a little bit about the Lustre monitoring tool. You're going to hear more about that from Chris tomorrow, so maybe I'll skip through that pretty darn quickly. And also Lustre LMT use cases. I want to pause a little bit and talk about I/O system balance, but this is just exactly what Doug was talking about, trying to make sure that you actually have enough I/O to keep your system in good balance. Then I'm going to start talking a little bit about the statistical properties of the data that we're collecting, and occurrence histograms is just the main tool that I use in that. And then I'm finally going to try to present to you a simple model of what's going on your system and how that simple model then relates what your workload is to the observations you get from LMT. So let's see. First of all, LMT, what is it? Well, you've got a computer. This is just very generic compute nodes on an interconnect. You've got your servers and your login node and some network out there that you're getting to it through. You run a daemon called Cerebro that is a little data transport. It's a very lightweight data transport daemon. LNT is actually plug-in libraries that run in Cerebro, and they're harvesting proc values, and then those proc values get sent over the external network to some external database server and get stuffed into a database. You get all sorts of stuff collected in LMT, all very useful stuff. We're going to focus mainly on bytes read and bytes written. So it's mainly, what I'm talking about is the bulk I/O data rates. So why would you want to do that? Well, the first use case, this is just a screenshot from my laptop of a website where I actually gather up all of the data. Like, okay, so you've got all these servers and all these LUNs, and you're gathering how many bytes moved. It samples at 5-second intervals, so every 5 seconds you're getting another number about how many bytes got read, how many bytes got written. You can add those up all across the servers, and that gives you basically a speedometer for your file system, how much is going on at that 5-second interval every 5 seconds. So here's 10 minutes of data, and I'm just connecting the samples with lines just so that it's visually a little more appealing. Red is the rate. Read rate, blue is the write rate. This is time on the x-axis. This is megabytes per second, I guess, on the y-axis. So you can do one of those graphs with the same kind of data. So again, time on the x-axis, megabytes per second on the y-axis, and you can compare that data with other data that you get in other ways. So these flat lines here, this is just what an IOR benchmark test. I'm sure most of you are familiar with IOR. So it's just the result of how many megabytes per second did IOR tell you your benchmark ran. So we're running 5 benchmarks that do some writes and then reads, writes and then reads, and writes and then reads. And LNT data then tells you what was happening dynamically behind that. And then there's also a third source of data being depicted here that's what's happening on the client side. That would use a library that instruments the IOR and tells you what the clients cumulatively thought was going on at the same time. So another use case is just to get a gestalt of what the whole day was looking at. So now I'm not connecting all the dots, all the samples with lines, because then it would just sort of fill in completely with color. So each of these dots is one of these samples over the course of a 24-hour period at 5-second intervals. So that's what, 17,000 something samples for reads, samples for writes. And so you just get a gestalt of what was happening on that file system that day. And you can see, sometimes things were going pretty fast. A lot of time, not much was going on that particular day. You can then take all of that data from that previous slide and collapse it into a single number for that whole day. How much I/O got read, how much I/O got written that whole day. And then you can map that again. We've got time on the x-axis, but now this is days, so over the course of many months, how much total I/O took place, so you can again get an idea that the workload is evolving over time. You've got some periods where there was just a huge amount of reads going on. This is basically 24 hours straight of reads at almost the maximum rate that the file system can produce. Happened pretty high once with writes, but for the most part the writes are not actually saturating at 24 hours a day. So I/O system balance, these are just some very schematic notions to try to present what Doug was talking about earlier. This is just your basic roofline model where you've got, how much money did I spend on my I/O system on the x-axis and how well does it perform on the y-axis, and then you would hope that you get more performance with more expense, but obviously it's going to flatten out at some point. So the question then is, how can you tell where that point's going to be? And the answer obviously depends on both the system that you're putting together and the workload that you're putting on it. So another roofline model, this time we're saying on the x-axis what's the load and how well utilized is the system. And again, you'd expect that as you increase the load, you're increasing the utilization until you get to some point. And job schedulers are really designed to try to keep you up here at this 100%, as long as you've actually got work to do. The job scheduler's job is to keep that resource completely utilized. But if you keep increasing the load, the actual throughput that you're getting, if you start getting lots and lots of I/O contention, even though the compute resource is 100% utilized all through that time, how much throughput you're getting is actually going to be decreasing if you've got way too much contention going on. And so there's sort of this hidden tax on the utilization that comes from having an imbalanced system. And so the idea here is, can you move that curve out a little bit so that you buy compute resource basically by buying I/O resource, and presumably cheaper, at least that was what one might hope. So again, this is just very schematic notion, time on the x-axis, and this is your cluster is the little links here. What I've got is green is any kind of job that's not really I/O intensive, and then you've got two jobs, one in red and one in blue, that are I/O intensive. So either one of these jobs can completely saturate your I/O system. So your I/O system is completely dedicated to fulfilling their I/O requests for the entire time that it runs. So the red job starts at this point, it goes along and it's firing away, doing huge amounts of I/O, and then it finally finishes, and then not long after that the blue job starts up and it goes. And what happens if the blue job started up right after the red job? Well, this amount of time to complete both of their I/O is going to be about the same. It's going to be completely saturated for the entire length of this time, but now they're both contending for those I/O resources, so they're each getting maybe only about half. And so that means that they're both sitting on those compute resources for that entire time. And so the amount of work that's not I/O bound that you can fill in around that is reduced. And that's where this hidden tax comes from. So we did sort of a case study back in April of 2009 where we changed the I/O infrastructure on the Franklin Cray XT at NERSC. And this is just a gestalt one day of LMT data from before. And this is another gestalt from one day of I/O activity after. And so you say, well, okay, sure, it kind of looks different, but which one was better, really? And were the workloads on the 2 days even the same? So are we really comparing apples to apples? Probably not. So that's where we start looking at the statistical view of this same kind of data. So here's the exact same before day, but now instead of having time on the x-axis, I've got the samples that you're collecting from your servers. Basically, over the course of a 5-second sampling interval, a server can move about 2 gigabytes. And so for each sample that you're actually getting in your LMT database, they could be up as high as 2 gigabytes or something smaller. So this is how many bytes was that sample, and this is the count of how many samples like that you saw. And as you can see, it's almost an angle iron here where almost all the action is happening at 0 bytes moved or very, very few bytes moved. And there are very, very few samples out here. You can't hardly even see them. So, it's kind of nice to put this in a log scale here so that you can actually see some of what the action is going on these lower probability samples. And also, just as an aside, on a log scale, when you get a straight line or something that's not too far from a straight line, that's an exponential relationship. So e to the minus x with whatever parameters. So the probability of seeing these samples looks like it might have some sort of exponential relationship. This is the after. Oh no, I'll take it back. This is one of the advantages of doing this kind of statistical gathering of the data is that you're not limited to just looking at 24 hours worth of data. So this is 30 days. This is a whole month of data, all still depicted with the same amount of information going into your eyeball. This is a little bit of an aside, but if you scale the histogram by how much data does that size transfer actually represent, then you get a better idea of what the impact is of I/O at these various, basically when the system is very busy and you're getting samples of 2 gigabytes, that's moving a lot of data. And in fact, you can actually see this is the exact same day as represented before. And now you can actually see that there is a little tiny bit of activity out there at the 2 gigabyte reads. So it does actually show up in the power spectrum, and that just gives you a little bit better notion of what the importance is. And this is, I guess, this is a 30-day gathering. This is just this is the after picture that we looked at before. So now we actually, from the before to the after, now you can see there really is a big difference. You looked at it before and you said, okay, I see these two things, but I'm not sure what the difference was between them. But now you can see there's a lot more action happening out here at the, more than half or more than two-thirds of the possible I/O bandwidth. A lot of the data is being moved out here. And in fact, you see this big ski jump here. There are lots and lots of data being moved at that 2 gigabyte sampling level. So this is just a way to emphasize the significance that these larger transactions really are important. So now we're back to 1 day's worth of data from before, and what I've done is just normalize the histogram so that now this actually almost could be interpreted as the probability density distribution for what the observations would be. And again, we're looking at now at 30 days. This is still before. So this is 30 days of data, and it's again just the normalized distribution. And then what we've got. Oh yeah, okay. So this is, and then this is the after. And so what we might hope is that over the course of 30 days before and 30 days after, your workloads might not have been too wildly different, and so you could actually have a better chance of actually comparing the two usefully. Oh, wait a minute. That's, sorry. This is 30 days before, this is 30 days after. Or 30 days of data from before, 30 days of data from after. So again, you can see that there's just a lot more action going on at where the file system is running flat out. So, there's still some question of, okay, well, is that just because the workload was that much bigger, or was it, or was it that the file system was actually able to perform better? And I can tell you it's not the point of this talk, but I can tell you that it really is the case that the file system was performing a lot better. I chose these two 30-day periods because the amount of actual data that was moved is about the same between the two of them. I think I saw Andreas with a hand. Oh, you're talking about these little low probability samples? I think that's just anomalies in the actual data collection. Might be. There were a few of them even before. You may be right. I don't know. I certainly haven't investigated why I get, these are very, very low probability events. And so, if you get out of 40 billion samples, you get 15 that look like that. I will look at it one day, but that's not on top of my priorities. So now we're going to look at a simple model of how this might go about. And so the idea here is in this, these are the observations you get out of LMT. And we can presume that there's also some distribution of what the transactions were that were coming from the compute resource asking for I/O. And so if we can, so this is going to be a simple model that characterizes what the transactions coming from the compute resource are, and then how would, theoretically, how would the data collection be reflected from the distribution of transactions that you have. So anyway, it's just a very simple model. We're saying that you've got almost 10 gigabytes coming in here. This is X. The X-axis again is time, and this is just sort of a block diagram to say that there's 10 gigabytes that are coming in here. It arrives at some random point in there. Again, the sampling interval is 5 seconds. We can get about 400 megabytes per second out of one of these servers, and so you can expect a little less than 25 seconds to process this whole request. And so you're going to get the LMT data is going to look like these 4 samples at 2 gigabytes, and then a little piece before and a little piece after. Some of the simplifying assumptions here, and these are, I'm sure everyone will say, wait a minute, it's highly unrealistic. Yes, I know that. First of all, I'm assuming that in one of these transactions, that is some sort of composite activity coming from the compute resource, all of the I/O comes in together. I'm assuming that the I/O subsystem goes as fast as it can, flat out, from the time it first knows that it has to do this until it's done. And finally, I'm assuming that when one of these transactions comes along, it's the only one, and we're not ever seeing multiple transactions, which obviously is not going to be the case in general, because the whole point here is that you have contention sometimes. But this is just a simple model to try to get some of the math down. So from now on, I'm going to actually talk about these samples as being, it's a 1.0 when you've got when you've observed as much as you can. So I'm just scaling it by 2 gigabytes. So you get 4 samples of 1.0, a 0.22, and a 0.76 out of this particular transaction. And if the transaction had actually arrived just a little bit later, you wouldn't get 4 of these 1.0s. You'd only get 3, and then you get these 2 big pieces, one on each side. So this is just the math relating how many observations you'd get given a transaction of a particular size. So the other possibility is, instead of having a transaction that's really long with respect to your sampling interval, if you have a transaction that's actually shorter than your sampling interval. So one possibility, obviously, is that this 0.76, I guess it is, 0.765, arrives so that the sampling interval can see the whole thing all at once, all in a single observation. And the other possibility being, of course, that it's split across 2 observations, and so you get a observation in your LMT data set of a 0.15 and a 0.615. Now, you can actually, for a given specific size of transaction T, you can actually calculate the probability that your observations that result are going to be any of these 1.0s versus some value that's less than 1.0. And for the particular example I was showing before, it was a little bit less than 10 gigabytes. This actually gives the actual relationship, but you'd get about 2/3 of all the observations from transactions of that size would be at the 2 gigabyte, and then about 1/3 would be less than that 2 gigabytes. Oh, okay, and then I just used, I'm going to refer to PA and PB later on. So this is just, these are the different cases. You break it out into the 4 different possible cases. And so P sub A is the chance that an observation is right at 1, and P sub B is the chance that an observation is smaller than 1, one of these n pieces, and this is for big transactions. And you can do the same thing for small transactions. So P sub C is the chance that the observation got all of T all in a single observation. In this case, again, for this particular example, P sub C is fairly small because the chance, if this is arriving at an arbitrary moment, the chance that it arrives such that it can fit entirely in here is fairly low. You only get about a quarter or something. And it's much more likely that it's one of these where you get 2 samples now split across this. So P sub D then is the chance that an observation that you have is one of the n pieces of one of these small transactions. So those are your 4 chances. Now let's go back and recall that I was saying it looked like there might be some sort of straight lines in the log scale distribution of the I/O, and so that implies that maybe just as a candidate, there's no deeply compelling mathematical reason yet why this should be, but if we just assume that the distribution of transactions that's being delivered to this system is in fact exponential, and in fact I'm just using the most simple exponential, so this is e to the minus x here, then you've got transactions, obviously most of them are small, but you've got this long tail over here where you've got transactions that are much larger than the observation interval. Then, so here now p sub a as a function of the set, this is the probability of, this is for transactions coming in given by this distribution, what is the probability of an observation at x for the case 1, the p sub a. And it's given by this expression. And since all of them are exactly 1, the probability density is then going to be infinite, but it's just a delta function that's given, the delta function at 1.0 that's given by this. The first thing I've done in this model is to say, well, okay, maybe the observation interval isn't perfectly exactly that value, but maybe it actually has, there's a little bit of variability in it. And in fact, that's not too unlikely. And so we can just superimpose a Gaussian on that delta function, and now you get this little Gaussian here. So now then the p sub b case, again, you've got this expression governs it. So this is the probability that transactions coming in of this, governed by this shape, and these are the transactions that are out here in the tail. The probability that your observations going into the LMT database are at some value x smaller than 1 is given by this. It's basically a uniform distribution and governed by this relationship. And I'm adding this one to this one, so that's why the little green sort of pokes up here. And then here's the p sub c case. So these are small transactions. So for some transaction that was in this region, what is the chance that the observation is? And again, this is the one where the transaction fits entirely within the observation. So you can see that out here near 1, it's very unlikely, but as you get close to very, very small transactions, it's almost entirely certain that you will see it as a single observation. And again, I'm adding the p sub c on top of these, and that's why this is actually 1 right here, so it's added onto there. So then here's the fourth case, the p sub d's. This is the chance that an observation that's smaller than the 1.0 is split. What the observation you're seeing is one piece of a transaction that got split across that boundary. And again, you can see that it's given by this relationship where now we're actually doing an integral over the entire distribution.